Good morning, good afternoon, good evening, depending upon when you're watching this video. Today we're going to cover pages 96 through 106 from our textbook. You should read those pages. There will be an assignment posted in Eraser, and also look in Eraser on the homework pages for information about a mini-tab assignment that does not come directly from our textbook. Today we want to talk about variation. Almost anything we measure, I guess I could say everything we measure, will have some variability in it. Usually not much. As an example, I have a picture up here of some soda water bottles. And if you would look across the top of these bottles, you can see what the fill is. Now it's easier to look across these fills than it would be to measure the fill with a scale or to measure the volume of the fill, but I can easily see that this bottle, the one on the right with the red liquid in it, that's probably strawberry, looks delicious, is filled a bit more than the second one, which is probably, I don't know what would be pale yellow like that. Whatever it is, I'm sure it's quite good. We've got a little more fill here on the orange and a little less fill again on whatever this color is. And this lemonade looks like it's just about the same as its neighbor to the right. Well, the point of that is not to think about delicious soda waters, but to think about the variation in the fill. And that's an important thing if we're manufacturing soda water to sell. Soda water, beer, whiskey, anything we put in bottles, milk, because we want to control the amount of fill in the bottle. We have some value that we're looking for, some average fill. Mu would be the population of fills for these bottles, and if it's a 12-ounce bottle, we want mu to be as close to 12 as we can get it. Now, usually we don't really know what mu is. We've talked about the difficulty of finding out what some of these parameters are, and mu is a characteristic of the population, so it's a parameter. So you know what we would do would be to pull bottles off the line, and we would see how full they are, and from that information we would compute x bar and use x bar to estimate mu. But an important part of that estimation is to know how much variability there is in x bar. Does our data tend to be close to x bar or far away from x bar? And that's an important thing to know about data. If you know that on a particular day in our bottle filling plant, we find that x bar, we take a sample and we find that x bar is equal to, say, 11.9995, about 12 ounces, right where we want it to be. But if you look at our data, you find that x1 was equal to 0, the first bottle we skipped, and x2, and we're not measuring what's in the bottle, we're measuring what was tried to put into the bottle. We're measuring the dispense, and x2 was 24 ounces. Then what happened here was an empty bottle, and what happened here was we filled the bottle to 12 ounces and then continued and overflowed, and so it went all over the floor and big mess. So not so good, but notice that these two would have an x bar of 12. So if all we knew was x bar, we might look at this morning and think, wow, that worked out pretty well. X bar is exactly what I wanted it to be. It's not enough to know about the center, the measures of central tendency, whether you're using the mean or the median or the mode or the mid-range or maybe some other measure of center that we haven't talked about. That's not enough. We need to know about the variability. And in particular in this chapter, we're talking about the variability about the mean. So we want to ask the question, is our data close to the mean or is it far away from the mean? and we want a mathematical measure, a quantitative measure. And so the measure we're going to use is the variance. And if we're talking about the variance of a sample, then we're going to use the English letter S with a little squared on it. And if we're talking about the variance of the population, we're going to use the lowercase Greek letter sigma. And just to complete the vocabulary before we do some defining here, we also will have the standard deviation as a measure of variability. And if it's of the sample, then we'll use the symbol lowercase s, no square this time, and it would be defined by finding the variance and taking its square root. And the standard deviation of the population would be just sigma, and that would be the square root of sigma squared. So let me scroll up just a tad here, and let's talk about how we would compute the variance of a sample. So sample variance. Well, let's just think about it. We have our x bar that we've already computed from x1, x2 through xn. That's our data set. And now I want to know if these data points, are they close to x bar or do they just spread out all over heck? So what if I would look at a data point and see how far away it is from x bar? So I would take each data point and see what the gap is between the data point and x bar. And then I could add those up. And if this is a tiny number, then these parentheses were small. If it's a big number, then the thing in the parentheses was big. A lot of variability or not so much variability. Well, there's 2 or 3 things that can go wrong with that, but that's the right idea. But there's a couple things that can go wrong. And one is, of course, if xi is below x bar, this is going to be negative, and if xi is above x bar, it's going to be positive. And so as I add these up, I could have negatives offset by positives, and I would get a sum. If they're perfectly offset, I'd get a sum of 0, which wouldn't tell me anything at all about the variability. It would tell me there was no variability. Well, that's not very useful. So somebody might say, well, why don't you just use the absolute value here, just the magnitude of the difference? That would have been historically something we could have done, but historically it was not what we did. What we did was to square this parentheses. When I square them, they're all positive. So now, if these are very tiny, then their squares will be tiny, and when I add them up, I'll get a small positive number. And if these gaps are huge, then when I square them, it'll be even more huge. Is huger a word? More huge. And when I add them up, of course, I'll get a big number. So a big number here would mean lots of variability. A small number would mean not so much. There's still one little flaw in that. and that is if I've got a really big data set, I could have small contributions for each xi, but whenever you add them all up, you could get a big number, indicating lots of variability, but maybe each individual had a very small amount of variability. So the solution there would be to normalize this sum by dividing by n minus 1. N is the number of pieces of data less 1. So this kind of normalizes what this sum is. And if we've got a lot of data, then we're dividing by a big number. If we've got a small data set, then we're dividing down here by a small number, and it kind of balances out what the computation of variance is. This is equal to S square. There is a challenge in trying to do one of these by hand, and that's just the computational burden. I would have to do a subtraction for each member of the data set, and when I do this subtraction, I'm have to get decimal digits, and then when I square decimal digits, that becomes even more tedious and adds to more decimal digits. You got to add them up. There's a big computation burden here. That would be significant if we were doing this by hand. There is an algebraically equivalent formula that if we're doing these computations by hand, and I hope you're not, other than teeny tiny sets that we use for illustration, but if even for a set of 10 or 12 data pieces, if you're going to do this by hand, it's going to be much better to use this formula: n sigma x squared minus sigma x squared divided by n times n minus 1. This has one subtraction in it instead of a subtraction for each data point. There's just one. You calculate this number, you calculate this number, and then you subtract. And so you're not fooling around with a lot of decimal digits, and very, very easy formula to use here. Totally equivalent to this guy right here. If we would just do the algebra on this formula right here, this is where we would wind up. Now, I want to take the time. I both want to take the time and I hate to take the time, but I'm going to take some time and do an example for you so that you've got an example. So let's just fill those soda water bottles. So let's fill the bottles. And as those bottles are filling, we pull some off the line and we measure how much liquid is in the bottle. And the first one we get off, we measure, and it had 12 ounces. And the next one had 11.6 ounces. And the next one had 11.9 ounces. And the next one had 12.7 ounces. And the one after that had 10.9 ounces. And still more. The one after that had 12.5 ounces. So that's our sample. And what's our sample size? 1, 2, 3, 4, 5, 6. And so our n was equal to 6. And let's find the mean and the variance. Well, I'm going to use this formula right here. So this formula, just look at the pieces. I'd have to know n. I do, n is 6, I just counted. And I'd have to know the sum of the data, sigma x. I'd have to know what that was. And so I'd add up this column right here, just add up these numbers. And then what else would I have to know? Well, I'd have to square each of these and then add them up. But if I computed n and sigma x squared, then I would have pretty much everything I need to plug into this and calculate what the variance is. So I'm going to propose that we add a column here and call it x squared. So if I square 12, I get 144. And if I square 11.6, I get 134.56. And if I square the next number, I get 141.61. And just in the interest of time, I'm going to do these two but not write them down. And I get, for 12.5 squared, I get 156.225. Okay. Now, you can get out your calculator at your leisure and verify that I've done this correctly. I added up this column, and when I added up that column, I got 71.6. And then I added up this column, of course not using dots here, but using the square of 12.7 and the square of, looks like that was 10. Can you read that? 10.9. When I added this column up then, I got 856.52, 856.52. So now if I take these two numbers and put them in this formula, I see that I've got an s squared that's equal to n, that would be a 6, times the sum of the x squared, that would be 856.52, so that would be a multiplication, minus the sum of the x's was 71.6, and then I'd have to square that, and that is over n times n minus 1 would be I'll write it as 6 times 5, but we know that would be 30, and the numerator will turn out to be, and I'm just putting this step down, so if you want to do it yourself, you can critique me or you can critique your own work, but you should get 12.56. I think that's pretty accurate. I did it a couple times. Over 30 is equal to 0.4187. 0.4187. That's I maybe would say approximately equal to, and that is what? That is s squared. Variance is 0.4187. Now, let's just think about what the units would be on this. Now, the units on x would have been ounces. So we'll put an OZ over here for ounces, 12 ounces, 11.6 ounces. If I square this number, then the units in the second column would be ounces squared. Well, you know, I don't have a real good feeling for what an ounce squared is. I know that would be the right unit, but that's not a unit that I use in daily life. It is the right unit mathematically, so we'll hang on to it. OZ squared. What do I get for the units on the variance here? Well, this would be just a pure number. Maybe I should do it up here. This would be just a pure number, and so it doesn't have units. Every x squared would have the units ounces squared, so when I'd add them up, I'd get ounces squared for the units on this component. This, when I add them up, would be ounces, but then I square that quantity, so again it's ounces squared. So what I have for this subtraction is ounces squared minus ounces squared divided by pure number again, and so the units are ounces squared, and that's just maybe a tiny bit, I would say, distasteful, because I don't know what ounces squared are, and if we had an example that involved money, we might wind up with a variance that was in dollars squared, and I don't know what that means either. So in order to avoid that kind of problem with units, most people, instead of using the variance as the measure, for the variability, we'll use the standard deviation, standard. And the standard deviation is just the square root of the variance. So usually we're going to be talking about the standard deviation, but we have to find the variance first. And so in this example, the standard deviation would be the square root of 0.4187. And maybe I'll just put OZ squared on there. And the result would be 0.64704. And the units would be back to the units of the original variable, ounces, because our original units were ounces. If this was a money example and X was in dollars, then our standard deviation would be in the units dollars. Whatever, if it was bushels, our standard deviation would be in bushels. The standard deviation for the population would be defined the same way. It would be the population variance, take the square root, and you've got the standard deviation. It is quite unusual that you would be calculating a population variance for all the reasons that we've talked about in the past. The concept is certainly in front of us. I can conceive what sigma squared would be. It would be the variance of the population, but I'd have a hard time computing that. Usually I'd be computing S and using S as an estimator for sigma squared. Nonetheless, I want to show you how to compute a population variance, because it's not the same computation as we use for a sample variance. A little bit of difference, and sometimes if you get those confused, occasionally that can lead to grief. And we don't need any grief. We've got enough grief in the world. So let me just write down what the formula would be for the population variance, and it would be, you're going to see that this is very similar. It would be sigma x. Now if we're doing parameters, instead of using x bar, which is an estimate of mu, I would use mu itself squared divided by, and not lowercase n, not a sample size, but the number of items in the population, and not minus 1. This was a minus 1. It was an n minus 1 when we calculated the sample variance. You can see right here in the definition of the sample variance, it was an n minus 1. If we're talking about the parameter population variance, you divide by n. Now, I'm not going to jump into shorthand for that, because you're not going to be computing that, especially not by hand. Somebody may give us 10,000 pieces of data and say, this is our population, compute the variance. Then we have to remember, number one, to use the formula sigma squared, not s squared. And number two, we got to remember to use technology, because nobody wants to do that much computation by hand. All right. Now, we got a new vocabulary and a new statistic here, the standard deviation. We'd like to get some feel, develop some feel for standard deviation. Some way to relate to standard deviation. And what I'm getting at right now is called the empirical rule, which says that if a population is normal, now we've tested for normality, we've talked about it, we haven't given a precise definition, but we should have an intuitive definition that normal means that our data peaks over the mean and falls off symmetrically to the left and the right and gives us sort of this bell-shaped curve. And you can think of this as just putting a smooth line over a histogram. And so a histogram of data that was actually normal, the histogram might look kind of like that, and I'll impose that bell curve on it because it's easy to draw. So those are intuitive ideas that we can make precise a little bit later. The empirical rule says that if I have, and I'm going to do this for a large sample, rather than for a population, if I have, and I'm going to draw a continuous curve because it's so much easier. So if I have my data, the histogram fits under this real nice. Just remember the histogram fits under this. And this would be, I'm going to call it X bar. X bar. If I would move up, now remember the standard deviation is the same units as X bar, and so I have no problem chopping off a little piece of the real number line in here that would be one standard deviation in length. And if I did that, I would be at a place, X bar plus one standard deviation. That's not a 5, that's an S, X bar plus S. And then I want you to come down the same amount, and you would be at X bar minus S. So the curve should look very much the same at these little vertical lines that I'm drawing, because if the data is normal, the curve is symmetrical. The empirical rule says that I should have 68% of my data between these two boundaries. 68%. If the data is normal, doesn't matter if it's the weight of newborn babies or the height of adult males, or I don't know, the length of bunny rabbits hopping around in a big field. If the data is normal between X bar plus S and X bar minus S, I should have about 68% of my data. And if you would just kind of continue this notion, and if you would move onto the right, one more of these, so this gap would be, this gap and this gap would be the same size, I would arrive up here at a point X bar plus 2S. And I want you to come down also one more standard deviation and arrive at X bar minus 2S. Then inside these red boundaries that I'm drawing right now, inside here, between these two, I should have 95% of my data if the data is normal. And if you would just continue this and come out to 3 standard deviations, X bar plus 3S, and then come down here to X bar minus 3S, inside here, inside X bar plus and minus 3S, you get approximately 99.7% of your data. That's the empirical rule. And actually it's a way that we can, rule of thumb, gauge if a data set is normal. We can take a data set that we just received, don't know anything about it, we can calculate X bar, we can calculate S, and then see how much data is between X bar and S. And if the data is normal, it should be about 68%. See how much data is between X bar plus and minus 2 standard deviations. Should be about 95% if the data is normal. And repeat for 3 standard deviations, and should be about 99.7. Now, I'm debating with myself here on what to show you next here, but let me bring in Minitab, and I think maybe I can just drag it over to where we're working right now and not share or reshare, and I'll kind of make it gigando. And the only thing I might want to do is move this like this. So I'm trying to enhance your viewing pleasure here. Okay. So this is a data set that we've used before. It's the first data set in the Nutriola data, and it's called body data. I'm sure that's the name of it, body data. And there are 300 pieces of data in here, or 300 observations, 300 rows, if you will. And I want to look right this minute at the weight, and I think we'll use the weight in pounds. And I want to use that as my data set and decide if that looks like it's normal data using the empirical rule. And that's not hard. Minitab made this thing a whole lot easier than doing it by hand. But my inclination is not to teach you how I did that right now. I just want to illustrate the empirical rule. So here's our data. It's weight in pounds, and you see we got a 217 pound person, and down here is a 190 pound person, and so forth. The standard deviation, well, we can find out what the standard deviation is. Let's do that. Let's go to statistics and basic statistics and descriptive statistics, and let's use the weight in pounds data, and I don't think we're going to separate that right now, and decide what statistics we want. Well, let's look at the mean, and now we know what standard deviation is, and so let's check standard deviation, and we know the median and the mode. We might as well look at all of those since we know what they are, and the min and the max, and how many pieces of data we've got. So I'm picking those off of this menu and saying OK. And then I've got, let's see, now we're going to do descriptive statistics for weight, and I pick the statistics I want, so I think we're all right there. We'll say OK, and this is the result. Weight in pounds. There were 300 pieces of data. The mean was 180.02, and the standard deviation was 43.37. So that'll be an important number for us. That measures the variability. Now, just because we're here, here's the mean and here's the median, and this is something we learned in the last lecture. I see the median is 177 and the mean is 180, so the mean is pulled a bit above the median. That would mean my data set's not completely symmetrical, and I've got a bit more weight on the heavy end, that's what's pulling the mean up, than I do on the skinny end of this data. If I wanted to find the range or the mid-range, I've got the minimum value and the maximum value, so I could add these two and divide by 2, and that would give me the measure of center we call the mid-range. And I see that the mode is 161.2, and that there were 4 observations at that modal value. So 4 people tied for weight at 161.2, and that was the most coincidence we had in weight, making that number the mode. And that number doesn't look very much like the median or the mean, so I don't know how useful that would be for us, but certainly in this course we define the mode. You know what it is and you know how to find it, even if we don't use it very much. All right, so if I'm going to use the empirical rule, then I need to know about the mean plus and minus 1 standard deviation, the mean plus and minus 2 standard deviations, and the mean plus and minus 3 standard deviations. And I need to go through this weight and see what percent of these weights fall in those 3 categories: mean plus and minus standard deviation, plus and minus 2 standard deviation, plus and minus 3 standard deviation. And here is some computation I did before class just to speed this up. And this is 1 standard deviation. And so by hand, I calculated what the boundaries would be for 1 standard deviation above and below the mean. And the B would be the count of people that fell in that category, plus and minus 1 standard deviation. That actually would be 137 pounds to 224 pounds. There were 211 out of the data set that fell into that box, and that turned out to be 70%. What did I say the guide was? 68%. So not too far off, huh? And this is 2 standard deviations. So how many of our pieces of data fell within 2 standard deviations? Well, 95.33%. Empirical rule said you should have about 95%. That worked out pretty well. And 3 standard deviations. Well, for 3 standard deviations, I got 99.33% of my data points were within 3 standard deviations of the mean. And so on this weight data, it looks like it's probably normal, at least based upon how well it fits the empirical rule. And of course you'll read more about that in your textbook. Sometimes we want to compare variability, like I might ask let's see where I can write and ask you a question here. I do want to write this down. What's more variable? Women's height or men's weight? Now, I've got a good feel for women's height. I mean, that has variability. Some women are tall, some women are medium sized, and some are short, and so I know there's some variability there. Men's weight, yeah, I see men that don't weigh very much. They're skinny people and maybe not real tall, and I see people that are both big and tall. I watch a lot of football, so on that front line, you're going to see people that tend to be big and tall. They weigh a lot. There's variability in men's weight. But which has the most variability? You really can't compare those things directly. And because you can't compare those directly, but because we want to compare them, we've defined the coefficient of variation, which we abbreviate CV, and which we define as the standard deviation divided by the mean times 100 in order to make it a percent. That is S divided by X bar times 100, so it will be a percent. Now, from two unlikely sources like women's height and men's weight, I can calculate the coefficient of variation for each, and then I can compare those, and I can say, oh, this one has more variability, or that one has more variability. And let me do that for you just real quick using Minitab, and you'll start to get the feel for what a great tool this is. So we're going to do some statistics, and they're basic and descriptive statistics. And now I want to look at, this is weight in pounds. Let's leave that up there, but let's add to that the height. And I'm going to use height in inches. The results would be the same if I use the metric system. But here I've got weight in pounds and height in inches. And this time I've got a bivariable because I'm asking questions about the results for men and the results for women. So I'm picking gender as a bivariable. Now let's go to statistics and pick out the statistics we want. And it would be nice to have the mean and the standard deviation, I think. I don't really believe I need the median, and it may just kind of get in the way, and I don't need the mode. Max and min, maybe we'll leave those there. But look right here, in the first little grouping, I've got the coefficient of variation. Now, I wouldn't need that there because I know the mean and the standard deviation can be obtained, and so I could compute the coefficient of variation, but I don't have to. Minitab will do that for me. So I think that's all the statistics we want. We'll say OK there. Double check here. We're going to be looking at weight and height for men and women. That's our bivariable. We've picked the statistics we want. Let's say OK. And here's our result. All right. 1 is equal to male. Gender, 1 is equal to male. So this is female. And this is weight. So the average weight, average being mean in this case, the mean weight for women is 171 pounds, and the standard deviation is 46 pounds. If we'll look at the height of men, the average is 153, no, that's the count. The average is 68.56 inches, and the standard deviation is 2.799. So what I'm telling you is this 46, the standard deviation of women's height, that would be women's weight, wouldn't it? I think I said we were going to use women's height. So this would be the standard deviation for women's height, 2.941, and the standard deviation for men's weight would be 38.91 pounds. The problem there was I didn't write anything down. I was doing that off the top of my head, but you get the idea. Height, women, standard deviation 2.9. Weight, men, standard deviation 38.91. You can't compare those directly, but you can look at the coefficient of variation, and I see that for men's weight, I have a coefficient of variation of 20.63. For women's height, I have a coefficient of variation of 4.62, which tells me that the weight of men is much more variable than the height of women. Of those two, if we're having a variability contest, the weight of men wins that variability contest hands down. Well, I've used so much time, but I'm going to just go ahead and just take another second of your time to review something that you'll need to remember whenever you start doing the Minitab exercise that I mentioned at the first of this video. And so I'm going to do a graph here for you, and I think we'll just do a histogram, and we'll do a simple histogram, and we'll do a histogram on pulse. I'm illustrating, so it doesn't, I'm not investigating anything, I'm illustrating, so it doesn't matter too much what I pick here. So, as always, let's put a label on our histogram. This is going to be pulse. We'll just keep this as simple as can be, no subtitle. I'll leave my initials on this, take responsibility for it, and just say OK. And here is small that up a little bit. Here's a histogram of pulse for men and women, and there were 300 that participated. And a question we might ask, does this data look normal? Well, a little bit, but not a whole lot. Looks like I've got more cases in this upper tail than I do in the lower tail. It does have a center mass here, which normal data would have. So it looks a little bit normal, but I would reserve judgment on how normal this is for right now. Notice that the pulses in this graph are marked at 60 and then nothing, and 70 and then nothing. Well, we know that these have to be the same width. And so the mark here that's not written would be 65. We can force that to be written if we want to, but it clutters the graph a little bit, so probably usually it's okay just the way it is. This would also tell me that my width of these bends was 5, because I'm going from 1, this would be the class mark or the midpoint, from 60 to 65, and so that would be a gap of 5. I can also hover, and I can see that this bar has a value of 57.5 to 62.5, so I could calculate the width from that, and that 42 individuals fell in this bar. Now these are 5 wide. Just suppose that I wanted to make it 2 wide instead of 5 wide. That may not be a good idea for this data, but knowing how to change the width of the bend certainly is a good idea for a data scientist or a statistician. So I right-click on the graph, and I edit the graph from the resulting menu. And I'm going to right-click again because I could edit any component of this graph. I want to edit the bars. And what I want to do is play with the bending, because I'm talking about how wide I want the bends. I want to change that. I'm going to stick with midpoint, and I'm going to specify the midpoints here, which will determine how wide. I'm going to take all this stuff out. I'm going to specify the midpoints. Now, if I want these to be, I think we said 2 wide, then I might have one of my midpoints at 40, so I'll type in a 40, and the next one would be at 42. So I'm going to put a space. The separator here has got to be a space. That's what Minitab demands. So 40, the next midpoint, I'm selecting midpoints, would be 42. Now, you know, there's a whole lot more than that, but when I'm doing the bending, Minitab will finish this for me. It'll know that we need enough bends to cover the whole range of data, and I've told it what the pattern is. I've told it that 40 is the center of one bend, and the next bend is centered on 42, and so it knows the width. It can do all the computations for us, so we're going to let it, and I'm going to say OK. Now it's giving me a reminder here that I didn't put in enough data, and it's going to have to take up the burden. It's kind of complaining, you're going to leave this to me again? And I am, so I'm going to say OK. And that gives me a new graph. And you know, in this case, I think that new graph may be worse than the one we started with, but it illustrates for you how to change the bending. So that's where we're going to have to leave this lecture. We've spent a fair amount of time on it. I thank you for your patience. feel free to watch these in 20-minute chunks if that helps you. You don't have to watch them all at one time. But this is where we're going to quit today. So thank you. The end. Fini. Have a good